Boolean Ring Cryptographic Equation Solving. This is work carried out with my co-authors Maura Paterson from Birkbeck, another part of the University of London, and Swart from the University of Cape Town in South Africa. So the problem we're going to be considering is a fairly general problem in cryptography. We have a system of polynomials f1, f2 up to fm, all simultaneously equal to 0, where the polynomials are polynomials over gf2 in the variables x0 up to xn, so in n+1 variables. We're going to assume without loss of generality that these polynomials are homogeneous. If we have a non-homogeneous system, we can always convert it to a homogeneous system by simply adding an extra variable in the appropriate way. We're going to assume that we have more equations than variables, and the equation system has a small number of solutions, and for simplicity, typically one solution. And in particular, we're going to be looking for a solution that does actually lie in the underlying field. So the solution is a vector of length n+1 over gf2. So, to summarise, we have a series of polynomials over gf2. They're homogeneous, and they typically have a single non-zero solution over gf2. One generic approach that has been used to address this type of problem is to add the so-called field equations. These are equations of the form xi squared plus xi is 0 for all the variables xi. So this has the effect of forcing the solutions to lie in the field gf2. So we end up with a non-homogeneous system, f1 equals f2 all the way up to fm equals x0 squared plus x0 and so on up to xn squared plus xn, and all those equations are required to equal 0. And then typically approaches to solving multivariate systems such as Excel and Grosvenor basis have been used on the original equations and these field equations. So we're going to take a slightly different approach. We're going to actually look at use the field equations to define what we've termed the Boolean ring. So this is the quotient ring of the polynomials over gf2 in the n+1 variables x0 to xn, and we're going to quotient that out by the ideal generated by these field equations, x0 squared plus x0, x1 squared plus x1, and so on, all the way up to xn squared plus xn. So we're going to quotient out by that ideal, and we're going to get a quotient ring which we've termed the Boolean ring B, curly B. And with this quotient ring, we can obviously define a canonical ring homomorphism from the original polynomial ring over gf2 to the Boolean ring with the kernel given by this ideal. So this is a mapping that takes a polynomial f and maps it in the quotient ring to f plus this ideal. This Boolean ring is a principal ideal domain, and it also has the property that for any element in the Boolean ring z squared equals z. So when we're dealing with the Boolean ring, we will typically use zi to represent the variables of the Boolean ring, where zi is the image under this mapping, under this Boolean mapping of xi. So we can write the original equation system, which was polynomials over gf2, f1 equals f2 ... equals fm equals 0. We can write an equivalent system in the Boolean ring, gamma f1 equals gamma f2 equals ... equals gamma fm equals 0. So we get a system of Boolean elements, not necessarily homogeneous, that are equal to 0. So at some points we'll look at this Boolean ring, address how we solve equation systems in this Boolean ring, and use this information to solve the original equation system in the polynomial ring. Okay, so to take a step back, the typical approach that is used for the polynomial ring solving equation systems over the polynomial ring, this slide is titled Excel approaches. Excel type approaches. These will also include Grosvenor basis approaches, say with the lexicographic ordering, are very similar. So the idea is we start off with our homogeneous equation system, f1 equals ... equals fm equals 0, and we take these original equations and we multiply them by monomials of a particular degree to generate a homogeneous system of some bigger degree, big D. We can represent, so we end up with a number of polynomials, and we're essentially considering a system given by the span of all these polynomials. So any resulting polynomial we get, we can obviously write as a row vector of coefficients once we've specified a particular monomial basis. If we write down a basis for the space of polynomials we've generated, we can write this down as a matrix called the Macaulay matrix. So we can express our system of polynomials that we've generated as one big matrix where the rows give polynomials that are a basis of this space. We can then use Gaussian elimination to find if it exists a bivariate polynomial in the span of the generated system. So essentially we would choose the two variables we were interested in to give the bivariate polynomial, and we would order the monomial basis so that they were, say, all on the right hand columns of the Macaulay matrix. So we have x0 and x1. We put all the monomials solely in x0 and x1 in the right hand columns of the Macaulay matrix. We can then use Gaussian elimination in the Macaulay matrix to try and find a bivariate polynomial, say an x0, x1, in the span of the generated system. If we have a bivariate polynomial, we can potentially factor that into linear factors by standard techniques, and one of these linear factors will give information about the solution. Essentially, one of these linear factors will allow us to remove one variable, potentially, from the equation system, so giving us a simpler equation system. So we homogenize the original system, which is what gives rise to the bivariate polynomial. If we hadn't homogenized the system, then we would do exactly the same thing, except we would then be looking for a univariate polynomial, which we could factor in the same way. So if we're unable to find a bivariate polynomial in the span of the generated polynomials, then what we can do is we can increase the system degree, generate more polynomials, and with the hope that the bigger degree, going to a bigger degree, will enable us to find a bivariate polynomial. But clearly increasing the degree d of the generated equation system makes the approach much less efficient. So ideally we want to keep this degree d as small as possible. Okay, so here's a very simple example. I have a polynomial system over, to give a general idea of what happens away from GF2, I have a polynomial system over GF37, f1 15x0 squared plus x1 squared plus 5x1 x2, f2 being 23x0 squared plus x2 squared plus 9x1 x2. And if I find out that 23f1 plus 15f2 is a bivariate polynomial, x1 squared plus 12x1 x2 plus 9x2, which factorizes into x1 minus 2x2 and x1 minus 23x2. So here, in this system, I could clearly substitute x1 for either 2x2 or 23x2. Okay, so the second bullet point gives another equation system. As you see further down the slide, this equation system is obtained by taking a simple invertible linear mapping of the first equation system. But this second equation system has we cannot generate a bivariate polynomial. So whatever form of lambda 1, f1 plus lambda 2, f2 I take, I can't generate a bivariate polynomial. But the equation system is essentially the same. The geometric structure is essentially the same. I've just used a linear mapping. Essentially, I've just moved the intersection points between these curves around in space. So ideally, an equation solving approach should be able to find equivalent factorizations for both systems. The second system would just have a factorization that had 3 terms in each of the 2 factors rather than 2 terms. So a geometric invariant approach should be able to find the factorization in both cases, but Excel and similar Grosvenor basis methods are unable to do this because they essentially have to be lined up. The factorizations have to be lined up in a very particular way with the coordinate axes. Okay, so we can actually construct a geometrically invariant generalization of the bivariate polynomial, which we've termed the Rank-2 Product Polynomial. And so I'll give the definition first. We can construct a matrix of partial derivatives for a polynomial f, and we say it has the Rank-2 product property if this partial derivatives matrix, say C sub f, has rank 2. So this is an easy matrix to construct. We just put the coefficient of the jth degree d minus 1 monomial in the formal partial derivative df by dxi. So each row corresponds to a partial derivative df by dxi, and each column corresponds to a degree d minus 1 monomial. And for a system f1 to fm, we attempt to find lambda 1 to lambda m such that this polynomial lambda 1 f1 plus dot 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 plus lambda m fm is a rank 2 product polynomial. Because if it is, then it can be factored. And we can attempt to do this by using these partial derivative matrices. You see, we would want the partial derivative, if the original linear combination lambda I fi is a rank 2 product polynomial, then the equivalent linear combination of partial derivatives matrices will be a matrix of rank 2. So we can potentially find such a thing by looking for matrices of rank 2 in the span of the matrices CF1, CF2 up to CFM. So we're attempting to find a matrix of rank 2, and a matrix of rank 2 has all 3 by 3 subdeterminants equal to 0. So each 3 by 3 subdeterminant will give a cubic system in the lambdas. So we can potentially find a solution for the lambda 1 to lambda m by generating a cubic system and then solving this cubic system, and that would then potentially give us variable substitutions. Okay, so over GF2, this is a definition of a rank 2 product polynomial. It's a homogeneous polynomial of degree d of the form the product of theta I dashed L dashed plus theta I double dashed L double dashed, where L dashed and L double dashed are homogeneous linear polynomials over GF2, and theta I dashed and theta I double dashed are constants in some extension field of GF2. So you can see what essentially has happened is it's a generalization of the bivariate polynomial in the sense that the bivariate polynomial just had two variables, say x1 and x2, and this is a generalization in that all we've done is we've mapped x1 to L dashed and x2 to L double dashed. So it's a generalization we get when we map single variables to linear combinations of variables. So in the example, we have a 3-variable polynomial with variables x0, x1, x2 over GF2, polynomial of degree 4, x0 squared and so on, plus x0, x1 cubed and so on, and that factorizes into L factorizes into L dashed times L double dashed times L dash plus omega L double dashed plus times L dash plus omega squared L double dashed, where omega is a root of y squared plus y plus 1 is 0 over GF2. So this has the form of a product polynomial. And if we calculate the matrix of partial derivatives CF, given at the bottom of the slide, we can see 3 rows because there are 3 variables, 10 cubic monomials in 3 variables. We write down the matrix, it's going to be a 3 by 10 matrix, and we can see here that it does indeed have rank 2. So we could identify the polynomial f is a rank 2 product polynomial just from its partial derivatives matrix. Okay, so we now have a definition. We're going to say a homogeneous polynomial f satisfies something called the Q-Criterion if its Boolean image gamma of f is quadratic or linear or 0. And the motivation for this definition is the following lemma. The Boolean image gamma of f of a rank 2 product polynomial f is either a linear Boolean element or a quadratic element of the form k dash k double dash plus k dashed plus k double dashed for some linear Boolean elements k dashed and k double dashed. So this is saying that if we have a rank 2 product polynomial, its Boolean image is quadratic or linear or potentially 0. So we can use the Q-Criterion to filter polynomials to find ones that potentially satisfy the Q-Criterion. The proof is fairly straightforward. We have our product form for the rank 2 product polynomial, the product of theta I dashed L dashed plus theta I double dashed L double dashed. We can multiply out those brackets. The leading term will be L dash to the power D. The last term, the final term, will be L double dash to the power D. And in the middle, we're going to have a sum of the form Ci, L dash to the I, L double dash to the D minus I, where the Ci's are elements of GF2. We take the Boolean image of this function, gamma of f. Well, that's going to be gamma of L dash to the power D, but that's just the image of L dashed. The image of L dash to the power D is the same as the image of L dashed in the Boolean ring. So essentially, whenever we have a power of L dashed or L double dashed and we take the Boolean image, we just get a linear term. So if we apply gamma to that polynomial, we are going to get a Boolean element of the form k dashed, the image of L dash to the D, plus the sum of C1 up to CD minus 1 times k dash, the image of L dash to the I, k double dash, the image of L double dash to the D minus I, plus the final term k double dash, the image of L double dash to the D. So depending on whether the sum of C1 to CD minus 1 is 0 or 1, I get the two cases in the lemma. But the point of this lemma is the rank 2 product polynomial, its Boolean image is quadratic of this particular form, or it is linear, or possibly 0. Okay, so we're going to be dealing with quadratic Boolean elements, and this definition in the first line has a generic form of a quadratic Boolean element. It's a sum of coefficients times zi, zj, where I and j are different, times terms of the form something times zi plus a constant a. So it has a sum of quadratic terms, a sum of linear terms, and a constant. So essentially what we're going to do is we're going to extract the quadratic coefficients and write them as a matrix. And we're going to write them as a symmetric matrix. And we're going to call this matrix partial G. So partial G has in its ijth entry the coefficient of zi, zj, or zj, zi. It's going to be a symmetric matrix, and it's going to have 0 diagonal. So the polynomial we already looked at of degree 4, f being x0 to the 4 plus x0, x1 cubed. If we take the Boolean image of that polynomial, we get gamma of f being z0 plus z0, z1 plus z0, z2 plus z1, z2. We have 3 quadratic elements, z0, z1, z0, z2, z1, z2, which is going to give rise to the partial matrix given there, 0, 1, 1, 1, 0, 1, 1, 1, 0. It's a symmetric matrix, and in this case we can see that this matrix has rank 2, which happens because the polynomial f is a rank 2 product polynomial, and this is its Boolean image. Okay, so generalizing that idea, we can say the quadratic element of the Boolean ring satisfies the R2 criteria if its partial matrix has rank at most 2, And as we saw in the previous example, a rank 2 product polynomial has a Boolean image, gamma of f, in the Boolean ring, which satisfies this R2 criterion. Sketch proof is, we know the image of a rank 2 product polynomial is of the form k dash k double dash plus k dashed plus k double dashed. The quadratic coefficient is of the form k dashed I k double dash j plus k double dashed I k dash j, which gives rise to the partial matrix which we can write as k dash k double dash transpose plus k double dash k dash transpose, where k dashed and k double dashed are vectors, column vectors of the coefficients of big K dashed and big K double dashed. So this partial matrix is the sum of two matrices, K dashed, K double dash transposed, and K double dashed, K dash transposed. Each of these matrices individually has rank 1. If we add two matrices of rank 1, we're going to get a matrix of rank at most 2. Okay, so we have this criterion that rank 2 product polynomials satisfy the R2 criterion. So what we want to do, and we have a method, obviously we can filter a big equation system by its Boolean images, looking for quadratic Boolean images. So what we want to do is we want to be able to find quadratic elements that satisfy the R2 criterion, quadratic elements whose partial matrix has rank 2. So suppose we have such a series of quadratic Boolean elements, G1 to Gm. We want to find a G in their span, say G is the sum of lambda I Gi, and we want their partial matrix of G, partial G, which is clearly going to be the sum of lambda I times the partial matrix of Gi, and we want this partial matrix, partial G, to have rank 2. So essentially what we're doing is looking for a matrix of rank 2, a matrix of low rank in the span of the matrices partial G1 to partial Gm. So this is an instance of a problem known as the min rank problem, finding a matrix of low rank in the span of some given matrices. And a method that can be used to address this problem is a method called the kernel method. So the basic idea of the kernel method is if we take a randomly chosen vector lambda1, sorry, a randomly chosen vector v1, and we're hoping that it's going to lie in the kernel of the matrix partial G, where we're hoping this matrix has rank 2. Well, a randomly chosen vector lies in the kernel of a matrix of rank 2 over GF2 with probability a quarter. So if the sum of lambda j times the partial matrix, partial Gj, if a vector lies in the left kernel of that, then we know that V1 transpose times this matrix obtained as the sum, which we can write as the sum of lambda j times the vector V1 transpose times the partial matrix dgj. That should equal 0 with probability a quarter. So it's quite easy to find matrices, to find vectors in the kernel, because the kernel, if we have a matrix of rank 2. Okay, so the coefficient vector lambda1 to lambda m satisfying the condition that the sum of lambda j times the vector v1 transpose times the partial matrix of gj is 0. Such a coefficient vector lambda1 to lambda m will lie in the left kernel of the given matrix. Block matrix, well, a matrix given by rows there, v1 transpose dg1 all the way down to v1 transpose dgm. So we can extend the idea, we can just add more material to this matrix. We can generate more random vectors v, v2, v3, up to, say, in this example, vl, and we end up looking for a coefficient vector in the left kernel of this given matrix. We end up solving lambda1 to lambda m as a row vector times this matrix, which is generated by random vectors v1 to vl and the partial matrices dg1 to dgm. So we just solve that is 0. So we can potentially solve that in a quite straightforward way by linear algebra. Furthermore, we can normally determine a good value of L. How many of these randomly generated vectors we need to take we can determine empirically. We discussed this in the paper. And furthermore, because these polynomials g1 to gm have been normally generated by some sort of echelon method, the partial matrices themselves dg1 to dgm usually have low rank, which helps. Okay, so suppose we've done this process, we've used the kernel method, and we found a quadratic Boolean element satisfying the R2 criterion. Well, then as this lemma says, then there exists homogeneous linear elements k dashed, k double dashed, such that G is k dashed, k double dashed plus k. If G takes the value 0 and k is not identically 0, then k takes 0, the value 0 with probability approximately 3/4. And that's quite easy to see. We've got three things: k, k dash, k double dash. We need them to satisfy the condition k dash, k double dash plus k is 0. There are clearly 8 possibilities for the values of k, k dash, k double dashed, and 4 of them give that expression being 0. And in 3 out of the 4 cases, you can see that k takes the value 0. So k takes the value 0 with probability approximately 3/4. We have to say approximately because we always have to rule out the identically 0 case, which happens with probability 2 to the minus n. Okay, so in fact, if we constructed an element G with partial matrix dg, partial G, having rank 2, the first 2 linear independent rows of this matrix give k and k double dashed. Any third distinct row is k dashed plus k double dashed. A matrix of rank 2 over GF2 can only have 3 non-zero rows. So that this actually gives us a method of constructing linear expressions, for example, of the form L is G plus k dash plus k double dashed, where k dash and k double dashed come from the partial G matrix. And these expressions L, L dashed and L double dashed take the value 0 with probability approximately 3/4. So here's an example of a quadratic Boolean element given by that expression Z0, Z0, Z1 and so on. If you calculate its partial matrix given there, it has rank 2. The first 2 rows give values of k and k double dashed. The third non-zero row corresponds to k dashed, k double dashed. And we can construct these expressions. We get 0, Z0, Z2 plus Z3, Z0, Z1 plus Z2 plus Z4 and Z5. This is an expression with 6 variables, so 64 points. If we rule out the all 0 point, we find there are 31 non-trivial 0 points for G, and on these 31 non-trivial 0 points, these 3 linear expressions do indeed take the value 0 for 23 of the 31 0 points. That's to say, we're probably approximately 3/4. Okay, so now we have a system G1 to Gm dashed, being 0 with non-zero solution Z star for quadratic elements satisfying the R2 criterion. And this means we can potentially find Boolean elements k1 to km dashed that are linear with corresponding coefficient vectors, which we can write as little k1 to little km0. And we can write this as 0 is k dash transpose, the coefficient vector, times z star, the solution, plus epsilon j, where epsilon j is a random variable that takes the value 0 with probability approximately 3/4. I'm sorry, there's a misprint there, and takes the value 1 with probability 1/4. So this is actually an instance of a well-known problem called the learning with noise problem. The BKW algorithm which is a form of structured Gaussian elimination, can potentially be used to address this LPN problem. So this, we can sum up what we've done in a process which we term the ECHAM2 process. Given a set of homogeneous polynomials over GF2, we find the image set in the Boolean ring B as Boolean elements. And then we then filter out and just look at the quadratic elements using the Q-Criterion and find a basis for these quadratic elements. And from these quadratic elements, we find the quadratic elements that have a rank 2 partial matrix, that's the R2 criterion. And from these rank 2 elements, we can potentially find many linear expressions that hold with probability about 3/4. And then this gives us an LPN problem with these probabilistic linear expressions, and we can attempt to solve this LPN problem using an algorithm like the BKW algorithm. So if there are insufficient linear expressions to solve this LPN problem, then we can go back to the original equation system and generate more equations by multiplying the elements by monomials to give a higher degree system. Okay, so the obvious question is, what kind of degree do we need to go up to solve these systems? Well, some papers by Fougere and others have argued this degree in comparable methods such as Excel and Grosvenor basis, say with the lexicographic ordering. It's given by the minimal value of d dashed in the series expansions of those polynomials. And we would expect the degree by the ECHAM2 process to be, in most cases, bounded by that required for the Excel algorithm. So initially we can kind of estimate a value for the degree of the polynomial for most equation systems by expanding this expression and looking at the coefficients. So as a proof of concept, we generated 63 homogeneous quadratics in n-20 variables. So this would have, each quadratic would have typically roughly 105 terms in. The XL polynomial has a negative coefficient of y cubed, which would indicate that we would expect to be able to solve this system by multiplying up to cubic polynomials. If we do this, we get a generated system of 1323 cubic polynomials comprising 1260 cubic polynomials and the 63 original quadratic polynomials. But these polynomials don't have any bivariate polynomials in their span. So an XL approach would usually require the use of quartic polynomials to address this system. If we use the approach outlined, the Boolean ring approach, we find the span of these cubic polynomials contains 183 polynomials that satisfy the Q-Criterion. When we take their image in the Boolean ring, we get the quadratic system. If we then use the kernel method to try and find partial matrices of rank 2 in the span of these polynomials satisfying the Q-Criterion, we did it with L equals 13, and in this case we got 1905 Boolean expressions, each taking the value 0 at z star with probability 3/4. And from this we were able to use the BKW algorithm. We split the variable space of 20 variables into 2 halves, each of 10 variables, and we were able, by focusing on one of the sets of 10 variables, so we just used 2 to the 10 counters to identify z star. Clearly it had a much higher count when we counted a particular property. So this process, which we term the ECHAM2 process, can identify the solution only going to cubic polynomials in this case. Okay, so a summary of the ECHAM2 process: we expect it in general to be more efficient than comparable methods because it's geometrically invariant, whereas comparable methods are not. The degree D required by the process to work should be bounded by the degree of comparable systems. And it should be much more straightforward, the processing, because we reduce the polynomial set to a much smaller quadratic system very early on. So we get rid of extraneous information that we don't need to process to get the answer. And furthermore, the ECHAM2 process shows a connection between solving a multivariate polynomial equation system over GF2 and solving an instance of the LPN-Problem, the learning parity with knowledge problem. Okay, so that concludes the talk. I see I've run a little bit over the nominal 25 minutes, which I apologise. I also see it's got very dark outside in the last 10 minutes, so I'm looking very dark in the video, which again I apologise. And if you're wondering where the name ECHAM2 comes from, in an earlier paper we had a process which we just called the ECHAM process. Here we specialised it for GF2, so we came up with the even geometric heuristic algorithmic method for GF2. And for those of you who don't know, ECHAM is also a small town just west of London and the location of Royal Holloway, where all three of us have worked at some time in our career. So, thank you.